2.6 Derivatives and Rates of Change. Let's start off by looking at the definition of the tangent line once again. In Figure 1, the blue line represents our slope between point P and point Q, which is our secant line. Our goal here is to find the slope of the tangent line at point P. In order to do this, what we do is move this point Q closer and closer to point P until it's so close that the 2 points are practically on top of one another. So then, by finding the slope between point P and that point Q that's so close to point P that it's practically touching it, we have a pretty good approximation of our tangent line, which is that red line. So that's what they're trying to say here, that we want to move this point Q really close to our point P and then find the slope between those 2 points to approximate the slope of our tangent line.
In other words, the slope of our tangent line is going to be approximated by the limit as our x coordinate approaches A. So here, as our Q, the x coordinate of our Q point moves really close to the x coordinate of our P point. And this is just a slope, y2 minus y1 over x2 minus x1. Let's go ahead and try this problem that we did in a previous section using our expanded knowledge by now. All right, so we have a function and we have our point, and if we look back, we wanted our A in this equation would just be the x coordinate of the point that we want to find the tangent line at, so that's just 1. Okay, and on the previous side we said that we're going to use the limit as x approaches A of f of x minus f of A over x minus A. Just y2 minus y1 over x2 minus x1. So we're finding the limit as x approaches 1 of f of x minus f of 1, right? Our A is 1 over x minus 1. And what is f of x? Just x squared. What is f of 1? 1 squared. Okay, so we have the limit as x approaches 1 of x squared minus 1 over x minus 1. Nice difference of 2 squareds on the top. Just factor that. And now that we cancel that out, we no longer have a 0 in our denominator, and so we can just substitute it in. So that means at this point we don't have to write that limit anymore, since we can just substitute it in, and we get 2. So our slope is 2. Let's look back at what our question asked us. Find an equation of the tangent line. We haven't quite done that yet. We have a slope. We have a point. Please remember this formula. Y minus y1 equals the slope times x minus x1. Okay, so let's just plug in our information. Y minus 1 equals the slope times x minus 1, and just y equals x2 times x minus 1 plus 1. We can just leave our answer like that and we're done. So now let's look at what we were saying before. The slope between these 2 points is just, if we call this point A, f of A, and this point x, f of x, then the slope between those 2 points is f of x minus f of A over x minus A, y2 minus y1 over x2 minus x1. So what would the slope of the tangent line be approximated by? That would just be the limit as our x point gets really, really close to our A point here. That's going to approximate our tangent line. So that's what we want to do. Another way to say this is if I pick some x-coordinate A and then I pick another x-coordinate really close by, A plus h, as I get these 2 points really, really close together, that would approximate my tangent line there. So what would the slope between P and Q be? That would just be y2 f of A plus h minus y1 f of A all over h. Now why? Because what is A plus h minus A? x2 minus x1. A minus A is just 0, so we just get h. Now, in order to approximate this tangent line, what do I want to find? The limit as what? I want my h to get really close to 0, right? Because as my h gets close to 0, I'm pulling the point that way. So in this one, I want my limit as h approaches 0. Both of these are really key. They're the two ways that we can approximate our tangent line. So, using that, let's find an equation of the tangent line to the hyperbola y equals 3 over x. I'm just going to write f of x equals 3 over x at the point 3, 1. So in this case, our a would be 3. Now, you can use either formula from here. I tend to prefer this formula, and the reason I prefer it is just because I have my h on the bottom and it's usually easier to cancel out. There's usually more algebraic manipulation involved in this equation, but again, depends on the problem, and sometimes you have to try one way. If you can't get anywhere, then you just try the other way. So since I'm doing the problem, I get to decide, and I'm going to use the limit as h approaches 0 of f of a plus h minus f of a all over h. You know what, I'm just going to do my a plus h on the side so I don't have to write so much out. F of a plus h would be f of 3 plus h, and that is going to be 3 over, instead of x, I have 3 plus h. And our f of a, which we're going to have to evaluate here, is just f of 3, which is just 3 over 3, which is 1. So we're doing the limit as h approaches 0 of 3 over 3 plus h minus 1 f of a all over h. Let's go ahead and get a common denominator on the top. I'm going to use 3 plus h. I didn't have to do anything to my denominator, but to go from a 1 over 1 to a 3 plus h, I need to multiply by 3 plus h on the bottom. Got to do the same on the top. Okay, so let's just simplify that. 3 minus h all over 3 plus h, and then I'm just going to multiply by the reciprocal. And remember how I said before, never multiply the bottom stuff out because hopefully something will cross out. What do you get on the top? 3 minus 3 is 0, so you just have minus h over 3 plus h times 1 over h. Yay, something cancels out. Probably did something right. So we have the limit as h approaches 0 of negative 1 over 3 plus h. Can you plug in the 0 at this point? Yes, you can. Negative 1 over 3 plus 0, which equals negative 1/3. Go back to the question. They asked us to find the equation. So we have a slope. We have a point. y minus y1 equals the slope times x minus x1. And all you gotta do is solve for y. Don't have to multiply this out any further, and that is your final answer. Here's just a neat little picture of it. Okay, so if we just do a little physics application, talk about it in a physics sense, instead of just saying our slope, let's call it average velocity, because that is our slope. Our average velocity is just the change in distance over the change in time. So this is nothing new here. This is just what we were looking at before. The instantaneous velocity is just going to be the limit as those 2 points get really close together. So here, this slide is pretty key. I just put together the average versus instantaneous velocity because this is what people mix up the most. The average velocity is just the change in position over the change in time. And again, the reason is just because this is a plus h minus a, which is h. The instantaneous velocity is the limit. So let's go ahead and consider a ball dropped from a height of 450 meters. Let's find the velocity after 5 seconds. And then let's find how fast the ball is traveling when it hits the ground. So let's call this A and this B. Okay. So remember the equation. You do not have to memorize this, but the position is given by 4.9 t squared. And in this class, we're going to use S of t for position. That's what your book uses. Another popular notation is to call it x of t. But for now, we're going to use this because that's what your book uses. We know that S of t equals 4.9 t squared. We want to find the velocity of the ball after 5 seconds. Okay, so let's start off with A, and let's do the velocity after 5 seconds. So we're going to approximate that by the limit as h approaches 0 of, I'm going to say S instead of F since we're using that, S of A plus H minus S of A all over H. And our A here is just our 5. So oops, I forgot to write my limit. Okay, and so let's just stick 5 plus h instead of our t. Minus, now let's stick in a 5. So I get the limit as h approaches 0 of 4.9 times 25 plus 10h, the outer and the inner, plus h squared minus 4.9 times 25 all over h, which is the limit as h approaches 0 of, let's see, we have a 4.9 times 25 plus 49h plus 4.9h squared minus 4.9 times 25 all over h. And this cancels out with this. So we have the limit as h approaches 0 of 49h plus 4.9 h squared all over h. Let's factor that h out of the top so that we can get rid of this 0 in our denominator. And now we don't have a 0 in the denominator. Use direct substitution, which is just 49. And our units here are meters per second. So that's it. Part B, how fast is the ball traveling when it hits the ground? Well, when does the ball hit the ground? The ball is going to hit the ground when it has traveled 450 meters, right? Because it's dropped from a height of 450 meters. So when S of t equals 450. So let's just do 4.9 t squared equals 450. If you did some algebra, you would get t equals 9.583 seconds. Please get in the habit of rounding to 3 decimal places. We need to do that for the AP exam, so we may as well get some practice. But it asks you how fast is the ball traveling when it hits the ground. So you're going to need to find the velocity after 9.583 seconds. So go ahead and do the same process that you did here, and you should get 93.915 meters per second. You can do that for practice if you want to see if you get the same answer. Now, another way to do this would have been that you would have read A and B and seen that you needed the velocity after 5 seconds, and then you needed to find another velocity. So maybe you just wanted, in general, an equation for the velocity. So let's go ahead and try that really quickly together. So our S of t is given by 4.9 t squared, remember that. And our velocity after t seconds in general can be given by the limit as h approaches 0 of S of A, or A in this case is just t in general, we just want a general formula, minus S of t all over h. And so we'll just plug it in. 4.9 t plus h minus S of t is just 4.9 t squared. And so we get the limit as h approaches 0. So in general, we just get that the velocity after t seconds can be given by 9.8 t. So let's just check our part A work. The velocity after 5 seconds would be 9.8 times 5, which is equal to 49 meters per second. Same answer we got. And in part B, we wanted to find the velocity after 9.583 seconds, and we should just get 93.915 meters per second. So now let's look, instead of being given an equation, we're given a table of values. Let's read the question. The temperature readings, T, in degrees Celsius, were recorded every hour starting at midnight. So here, this is midnight. The time x is measured in hours from midnight. Find the average rate of change of temperature with respect to time from noon to 3. So noon is going to be 12 hours after midnight. So from noon to 3 is going to be between time 12 and time 15, right? So we just want to find the slope. So here, all we're going to do is we're going to do T of 15 minus T of 12 all over 15 minus 12, and that's just going to be, let's see, 18.2 minus 14.3 all over 3, and we should get about 1.3 degrees Celsius per hour. Do not forget your units. Your units are very important. In the AP exam, you will lose 1 entire point for not putting units. All right, from noon to 2, we're going to go between 12 and 14. So the same thing, T of 14 minus T of 12 all over 14 minus 12, and that's just going to be 17.3 minus 14.3 all over 2, and we should get 1.5 degrees Celsius per hour. And then from noon to 1 is just going to be between 12 and 13. And that's just going to be 16 all over 1. And we should get 1.7 degrees Celsius per hour. Okay, so that part wasn't too bad. Estimate the instantaneous rate of change at noon. Okay, there are 2 ways to do this. The first way I'm going to say, since we're looking at the table right now, well, I want to find, okay, I'm looking right here. How might I approximate the slope? Let's just say we're given this graph, right? And I want to find the instantaneous velocity right here. Okay. By this table, I'm pretty much given the slope between any 2 points. How am I going to use this to approximate our tangent line? This. Say I'm given this slope here, okay? And say I'm given this slope here. Let's call this A. Let's call this slope between these 2 points B. If I average slope A and slope B, aren't I going to get a pretty good approximation of what's in between the 2 of them, that instantaneous velocity there? So what am I saying? I'm saying if I take the average slope between these 2, and then I take the average slope between 12 and 13, I'm just going to put them next to each other. So if I say this is slope 1 and this is slope 2, and if I take the average of slope 1 and slope 2, aren't I going to get a pretty good approximation of this instantaneous velocity? I would say yes. So let's go ahead and try that. So I was saying, let's go ahead and find this slope, and then let's find this slope. Let's call that slope 1 and this slope 2. We'll average them to find this. So I'm just going to write at the top here, M1 can be given by 14.3 minus 12.1 all over 12 minus 11. So I get 2.2 over 1. Okay. And then our slope 2, we've actually already found to be 1.7 degrees Celsius per hour. If I want to approximate the instantaneous, I'm going to approximate that as the average of the slopes. So that is just 2.1 plus 1.7 all over 2, which is 3.9 over 2, which is about 1.95 degrees Celsius per hour. So now another way to do this would have been to plot everything out, and then we want to find the instantaneous velocity at 12 seconds. So this is just the plot. In order to find this, what is this triangle deal? This triangle deal is just saying, okay, let's go ahead and draw a nice tangent line in. So we have to draw things really, really well in order to make this work. And then you just have to pick 2 points. So let's say we pick this point here, 14, and then let's say like 18.1. And then let's pick this point A, and let's say, I don't know, it's like 8.7, and the y-coordinate is 8. So if we do this really well, we could approximate our slope by y2 minus y1 over x2 minus x1. And that would give us 1.906 degrees Celsius per hour. So, we can say approximately our instantaneous rate of change of temperature with respect to time at noon is 1.9 degrees Celsius per hour. It's pretty much a consensus we've got from both ways of doing it. Now let's just formalize the definition of the derivative. Well, the derivative of the function f at a number a can be denoted as f prime of a, and that is just that same limit. And we said before that the limit either this way or this way yields the same results. And so that is how we define the derivative at a, f prime of a. So let's go ahead and look at an example. Find the derivative of the function f of x equals x squared minus 8x plus 9 at the number a. So what we want to find is f prime of a. And let's go ahead and use my favorite of the two formulas. As h approaches 0, of f of a plus h minus f of a all over h. And I'm just going to work out f of a plus h on the side, just so I don't have to write as much. A plus h, because we have x squared, minus 8 a plus h. We're sticking in the a plus h for the x, plus 9. And I'm just going to simplify that. Okay, and f of a, of course, is just going to be a squared minus 8a plus 9. So let's just plug that in. So we have the limit as h approaches 0 of a squared plus 2ah plus h squared minus 8a minus 8h plus 9 minus this whole thing. So I'm just going to switch all the signs. And so my a squared cancels out with my a squared, and my minus and a plus and a plus and a minus. So we end up with the limit as h approaches 0 of 2ah plus h squared minus 8h all over h. We can factor an h out of the top. They cancel out, so now we can just use direct substitution. 2a plus 0 minus 8. So our answer is just 2a minus 8. And that is the derivative of this function. So our earlier work on tangent lines together with the definition of derivatives gives us that the tangent line to y equals f of x at some point a f of a is a line through a f of a whose slope is equal to f prime of a, the derivative of f at a. Just saying that the tangent line, the slope of the tangent line is f prime of a. So let's just look at that in a picture, the picture that we've seen a couple of times now, explaining our two definitions and how they mean the same exact thing. We just want to pull this other point really, really close to P so we can approximate that slope of that tangent line. And now we're saying that is just the definition of f prime of a. The point slope form is y minus y1 equals the slope times x minus x1. We can write an equation of the tangent line to the curve. So we have this function and we have a point, and we know our slope can be given by the derivative now. So we can find the equation of the tangent line through a point. So using that, find the equation of the tangent line to this function at the point 3, negative 6. So we need to find f prime of 3 because that's our a. So what is f prime of 3? Well, you'll notice that this is the same equation that we used in example 1, where we found that f prime of x was 2x minus 8. So f prime of 3 is just going to be 2 times 3 minus 8, which is negative 2. So we have a slope, we have a point, and so we have an equation. Y minus y1 equals the slope times x minus x1. Y equals negative 2 times x minus 3 minus 6. We're good to go. Next problem. Oh, here's a graph of our solution. So let's just take the interpretation as a rate of change. The derivative, f prime of a, is the instantaneous rate of change of y equals f of x with respect to x when x equals a. So it's just instantaneous rate of change as opposed to the average rate of change, which would be the secant line. Note that when the derivative is large, the y value changes rapidly, and when the derivative is small, the y value changes slowly. So that's all we have there. Just some notation. The position function is going to be given by s of t, and that's just the position along a straight line, and we're just using that from our book. On the AP exam, it's usually denoted by x of t, but you'll get used to that. The velocity is always given by v of t, and that's just the derivative of the position function. And now the speed. The speed is just the absolute value of the velocity. That's what speed is. Speed always has to be positive. It is the absolute value of velocity. The difference between velocity and speed is that velocity tells you something about the direction the particle is moving in. It'll be positive if it's we'll say positive for moving to the right if it's just along a straight line, and negative would be moving to the left. Also positive would denote that it was moving up, and negative that it was falling down. Speed always has to be positive, so it tells us nothing about the direction of travel. So let's look at one final example. The position of a particle is given by the equation of motion S equals f of t, which equals 1 over 1 plus t. I'm just going to write S of t equals 1 over 1 plus t. That's my position function. Find the velocity and speed after 2 seconds. So I want to find the velocity after 2 seconds, which is just the derivative of the position function, which equals the limit as h approaches 0 of s of a plus h. So our a in this case is 2. Minus s of a all over h, which is just the limit as h approaches 0 of 1 over 1 plus, instead of t, I'm putting in a 2 plus h, minus s of 2, 1 over 1 plus 2 all over h, which equals the limit as h approaches 0 of 1 over 3 plus h minus 1 over 3. So I'm going to get a common denominator. And so that's going to just be 3 times 3 plus h. To get from this denominator to this one, I need to multiply by 3. To get from this denominator to this one, I need to multiply by 3 plus h. 3 minus 3 is 0, so I have minus h on the top. I'm just going to multiply by the reciprocal. Cross those out. Now I can apply direct substitution. I don't have a 0 in the denominator anymore. Negative 1 over 3 times 3 plus 0, which is just negative 1/9. And that's in meters per second. Don't forget about your units. So the velocity after 2 seconds is just negative 1/9 meters per second. And so the speed is just the absolute value of the velocity. And that's just going to be 1/9 meters per second. That's it for this lesson.